classes today, we've talked about several gas laws. Name one.
Avogadro's constant.
That's not a law.
Dalton's law.
Dalton's law. Boyle's law. Amonton's.
Charles.
All right. That is so much to remember, so we have to keep it much simpler. We're going to continue. We're going to continue talking about gas laws, and the gas law that we are going to talk about today, falling all into our big idea, is known as the ideal gas law. We're going to combine all of these gas laws into a single statement that relates pressure, volume, moles, and temperature. And we will introduce a new constant known as the universal gas constant, R. Couple things you have to remember in this section. The pressure unit will determine which R you select. If pressure is in atmospheres, the R that you will select is 0.0821 liters atmosphere per mole Kelvin. So if the pressure is in atmosphere, look at the R's. Pick the R that has atmosphere built into its complex derived unit. If the pressure is in kPa or pascals, if it's in pascals, you'll convert to kPa. Once you're in kPa, you will use this R, 8.314 liters kPa per mole Kelvin. And if pressure is in torr millimeters of mercury, you will use this R. And all of those quantities for R are provided to you on the back of your second semester periodic table, so you don't need to memorize them. Again, whatever unit of pressure you're given will determine which R you select. One thing you really need to be aware of is the volume must be in liters, and the temperature, just as you have seen throughout this entire unit, must be in Kelvin. Must. Okay? PV equals nRT is known as the ideal gas law. Pressure times volume, pressure and volume being inversely related according to Boyle's law, is equal to nRT, where N is the number of moles of gas you have. Couple variations with the ideal gas law that I want to introduce up front, and then we're going to be walking through 6 examples to make sure that you can apply the ideal gas law. So the ideal gas law is PV is equal to nRT. Now in the lab, we use balances. We get mass in grams. Let's say, for example, that you had 20 grams of oxygen gas. If we wanted moles, we would simply divide by the molar mass. 1 mole of oxygen gas has a molar mass of the following, and then we would get some answer in moles. This is the mass in grams. If we divide the mass in grams by the molar mass in grams per mole, we have moles. So one other way we can write the ideal gas law is we can replace moles with mass over molar mass. So one variation of the ideal gas law is the following. if you interchange these two variables, and we've talked about the fact that you can interchange the numerator on one side of the equation with the denominator on the other, you get PM is equal to mass over volume RT. What is mass over volume equal to? Density.
Density is what I meant. Gather density.
And here's your other formula. That is one cute little way to remember it. Some girls suffer from PMS, and boys can be very dirty sometimes. So that's another way you can remember it. Ideal gas law, 2 variations. And now we can use one of these 3 formulas to solve a whole bunch of problems. Joseph?
Is that M divided by M and the math product divided by RT, or is it MRT divided by M?
Whoa.
Actually, it doesn't matter. And I'll show you why. If you have 1/2 and 5 times 4 here, are you with me? 1/2 of 20 is 10, right? And if you do this instead, that's 10 also. So it's the same thing, correct? Yes, yes? Joseph, yes, yes? All right. So it doesn't matter. So those are your formulas. Keep them in front of you as we work through a few problems together, and then we'll see if you can do it. And I know you will. All right. First problem. Let's read it, and we'll get the information down. It says 0.0300 moles of gas occupy 500 mils of space at 2 atmospheres. Calculate the temperature. So they gave us 0.0300 moles, so that's N. And the volume is 500 mils, but one thing I said to you right away is we are going to need to get to liters. Move the decimal 3 to the left to go from mils to liters. Remember that 1 liter is 10 to the 3rd milliliters. That's something you need to know. We've got a pressure of 2 atmospheres, and we want to know the temperature, and they didn't ask for a specific unit. It's going to pop out in Kelvin. Leave it that way. Which R should we use?
The one with ATM.
The one with ATM in it. So 0.0821 liters times atmosphere over moles times Kelvin. And now we're ready to rock. I am going to use PV is equal to nRT because they gave me moles. And if I want temperature, I'm going to divide both sides by what? nR. Pressure, volume, universal gas constant, and you don't have to write it there as well. We just did that initially until you get comfortable selecting it, which is not going to be a problem for you. Remember, if you have more than one variable in the denominator, you will need the red parentheses in your calculator. So you have 1 divided by open parentheses 0.03 times 0.0821 close equals, and you have 406 Kelvin. And again, once you pull your variables out, make sure the volume is in liters. If you're given temperature, make sure that's in Kelvin. And then it's just a plug and chug situation. And I think you'll be very, very solid in this type of simple calculation.
Did that number come straight from your calculator?
Uh-huh.
You don't have to convert to, like, it doesn't give
It
you-
didn't ask how they wanted the unit, so I just let Kelvin fall out. If they asked for degrees Celsius, subtract 273. Easy peasy, yes, yes? All right, let's do another one, equally as easy. And I'm going to write my formulas up here so we can determine which one to pick. Excuse me. Alrighty, on number 2, it says argon occupies 100 mils of space. What does that 100 mils represent? Volume, and we don't want mils. Watch your siggy wiggies. Alrighty, we have 80 degrees Celsius, and what does that represent? But we don't want degrees Celsius. And we have a pressure of 203 kPa. We want to know the mass of argon, little m for mass. We want little m. So I'm going to use this formula. Now be careful with the variable manipulation. Some of you are very strong here, others need a little more work. If I'm solving for little m, I need to first multiply both sides by big M and then divide both sides by RT. Where do I get the molar mass of argon from?
the period.
You got it. Pressure, 203 kPa. Volume, R. Gotta figure out which crazy R we want. Which R do we use? The one with kPa, 8.314 liters kilopascals per mole Kelvin. And I really want to look at the unit cancellation here. It's crazy. Mole, kPa, liter, Kelvin. Left in the unit of grams, which is what I want. And again, the only parentheses you need are the ones on the bottom. How we doing? Pretty good? All right, let's try 3 together. On 3, it says 6.29 grams of carbon dioxide. That's my mass. Occupy 10-liter container. Now that they gave you in liters, so don't do anything silly. The temperature is 100 degrees Celsius or 373.15 Kelvin. We want to know the pressure in torr that the carbon dioxide exerts on the wall of the container. What formula should we use? You could use PV equals nRT, but it might be easier to use the one that has mass in it. But you can use either one, it's okay. You just have to do a whole nother piece. If I want to solve for pressure, I'm going to divide both sides by V. So I'm going to extend this out and put volume there. I've got 6.29 grams. Which R do I pick? The one with torr in it. Ooh, where do I get the molar mass from? So for carbon dioxide, 44.009 grams per mole. Let's look at the crazy units. Grams. Moles are in the denominator of both. Here's why you need liters. Kelvin. And we're left in a unit of torr, which is a unit of pressure. I need those parentheses in the denominator. I have 6.29 times 62.4 times 373.15 divided by open parentheses 44.009 plus, not plus, times 10. Close. And I have 333 torr. So far, so good? Try number 4. Number 4 says, it's at the top of the screen, calculate the molar mass. No, let's do 4 together. On number 4, because this has density in it, so let's do this one together and the next 2 you can try. On number 4, it says, calculate the molar mass of a gas that exerts 2.50 atmospheres of pressure. The temperature is 423.15 Kelvin, and the density is 0.780 grams per liter. So with those variables, what formula should we use? Our dirty one, right? And what do I want to solve for? So I'm going to divide both sides by P. I've got this density Ooh, which R do I need? The one with atmospheres in it. And again, if you really look at your units, you'll see what you're left with at the end, which is grams per mole. Yes, yes? I would like you to try 5 and 6, which is at the top of your screen. How we doing? Did you get number 5? So on number 5, you want to calculate molar mass, but the density isn't given. So I would use the PV is equal to little m over big M RT. If they gave you density, then you, or looking for density, then you would use the density formula. and look up only when you have the answers, okay? Don't look up unless you have the answers. How we doing? Got it? 5 and 6? Yes, yes? Ideal gas law is critically important. And I mean, you can link this back to Stoic. For example, when we did limiting reagent problems, you were always given mass in grams for both. Well, if you had a gas, you might be given all the variables of the gas except moles. You'd have to figure out moles from the ideal gas law and then compare it to the others. So ideal gas law, really, really important, and there's a lot of different ways we can integrate it in. The problems that go with what we talked about today is classwork 3.2b, 4 through 10. All right, so ideal gas law, PV equals nRT, allows you to link 4 variables together. In the lab this week, you will be using the ideal gas law, and it's probably the only time you will try and validate R, the universal gas constant. And we'll talk more about the lab later in the week. It's really a very cool one. I think you will enjoy it. Questions here? All right, so ideal gas law, PV is equal to nRT. And again, you pick R based on the units for peak.